And thanks, Patrick and William, for the invitation. So the general point I would like to get across tonight is that we can use nanophotonics to shape and enhance spontaneous emission from high energy particles, such as X-rays and free electrons. And I will try to convince you with a combination of theoretical and numerical analysis and tools that we can use to describe fundamental light matter interactions that involves high energy particles, and experiments in two distinct platforms using free electron beams and X-rays. And so I will also essentially cover some of the work I've done during my PhD with Marin at MIT, and also more recent results towards the end of this talk in collaboration with Ido Kaminer from the Technion on what we call now nanophotonic scintillators, and especially their application in X-ray imaging. So typically in nanophotonics, we work with what we call nanophotonic structures. Well, let me just try to get rid of that closed caption thingy over there so that you can see the titles of my slides. Okay. All right, that's much better. So in nanophotonics, we consider what we call nanophotonic structures. And their main characteristics is that they're patterned at the scale of an optical wave. And due to that, they significantly modify the way that light propagates through them, and typical properties that we think in terms of microscopic terms like reflection, transmission, scattering can be significantly altered by those structures. Inversely, the same structures can be used to enhance the amount of light emission from typical emitters, like a dipole emitter, via, for instance, what we call personal enhancement. And in personal enhancement, we can essentially shape and enhance the distribution of light from spontaneous emission by engineering the local density of states in such a nanophotonic structure. And this fundamental physics has led to an enormous amount of effort in realizing this physics at the nanoscale, and therefore realizing many different types of nanophotonic structures that can emulate this physics in 1, 2, and 3 dimension from very many groups across the US and the world, free form and periodic structures, and also reconfigurable ones in some cases. Thanks. What has also been driving this interest in fabricating the structure is a few very exciting applications, such as novel light sources and laser sources enabled by nanophotonics, the possibility of shaping light locally at the nanoscale with flat optics and metasurfaces, doing photonic computing with reconfigurable arrays of waveguides, shaping and enhancing the way that materials absorb and emit light, for instance, in thermal emission and photovoltaics, and more recently, combining concepts in high energy particles, for instance, doing particle acceleration on a chip with nanophotonic structures. And so tonight I will zoom in on a few of those applications that all have the following thing in common. They involve radiation from a high energy particle. And this form of high energy radiation can be used either just as a simple light source, for instance, in the case of on-chip free electron driven emitters, or we can look at the emission from high energy particles as a diagnosis tool, for instance, to detect or get an idea of what the characteristic of the beam of high energy particles, such as free electrons in the case of, for instance, Cherenkov detection, or X-ray in the case of your average dental X-ray, where scintillators are used to convert X-rays into visible light to make an image. And I will talk mostly today about fundamental physical effects that might lead to interesting and novel integrated light sources driven by free electrons and other types of high energy particles that can span a very broad spectrum, and with tailored optical properties by engineering the nanophotonic structures that they interact with. And also new types of particle beam detection and diagnosis tools that rely on nanophotonics to get more information from the light that's emitted, for instance, with an X-ray. And one of the applications that we're particularly excited about is to make, for instance, high resolution and fairly low dose, so efficient X-ray imaging applications. And I will talk about that towards the end of this talk. And so I will start with some general considerations on free electron light interactions. And I will also present a setup that I built during my PhD to study and record them with free electrons in a refurbished scanning electron microscope. And then I will focus on two independent realizations of nanophotonics enhanced radiation from two types of high energy particle, mostly free electrons and X-rays, although those concepts might generalize to other types of high energy particles. Okay, so let's get started. So typically when we think of free electron light interaction, we have the following picture in mind. This is you're inside the vacuum chamber of our scanning electron microscope. It's typically focusing a beam at a given height. And we put a sample in the path of the beam, typically at this very small angle so that the beam intersects or hits the sample. There is light that's emitted. I'm gonna tell you in a few slides what type of effect can lead to light emission from free electrons. And this light is directly detected with free space optics that are inside a vacuum chamber in our case. And then we do spectroscopy and analysis of the emitted light. And so there are several fundamental effects that can lead to spontaneous emission from free electrons. Interestingly, they were all discovered in the past century or so. And in the following, I will refer to them as cathodoluminescence, which is a general term referring to radiation from free electrons. They're typically split into two main categories, coherent and incoherent cathodoluminescence. And from an electromagnetic perspective, the only difference really between them is the form that takes the polarization induced by the free electron into the material. So let me be a bit more specific here. So let's start with the coherent cathodoluminescence. So perhaps an effect that you already know is the Cherenkov effect. It's a Nobel Prize winning discovery. It's very well known, especially in particle physics. And it has many analogs in other fields of physics. It happens when a particle propagates at a speed which is larger than the phase velocity of light in the material. So you typically need a refractive index which is larger than 1. And at this threshold condition, electrons can emit spontaneously plane waves. And the dispersion relation of that particular effect is pretty well known because you get a conical wavefront, which is analogous to the shock wave you see when an aircraft flies faster than the speed of sound in air. The other effect, which is an analog of Cherenkov in periodic medium, is called Smith-Purcell effect. And there you have discrete translational invariance of the permittivity, which forces photon emission into Bloch waves. So typically when we talk about Smith-Purcell effect, we're interested into the radiation that goes into the far field, and that follows also a pretty well-known dispersion relation that typically relates the wavelength of the emitted light to the angle of emission and the periodicity of the grating to first order, just from energy and momentum conservation. There is an intuitive explanation for why electrons emit in this particular setting, which is particularly relatable for metallic gratings, where when the electron flies above the structure, it's going to induce some polarization or image charges inside a grating that have the periodicity of the corrugated grating. So you can polarizations that can emit coherently into the far field, given some dispersion relation. There are two other effects in coherent cathodoluminescence I will not talk too much about tonight, so I'll just go through them very quickly. Transition radiation occurs when the electron passes through a discontinuity in the permittivity. And in some cases, this type of flight through a discontinuity can also result in the excitation of surface waves, such as surface plasma polarity. But what's common to all of those effects in coherent cathodoluminescence is that they can be described by a current source, which in type domain follows the flight of the electron, and which we can look into frequency domain as well, where you see that we have this complex exponential that has the speed of the electron inside. And an interesting thing that we can already notice is that this wave vector into the exponential is larger than any free space wave vector. So we will need an additional kick from nanophotonic structures in order to get light emission or phase matching. For instance, in Cherenkov, this additional kick comes from the fact that we add the refractive index, and in a periodic structure, it comes from the discrete translational invariance. So we have the block wave vector is defined up to some harmonics of the periodicity. The picture is very different when we look at what's called incoherent cathodoluminescence, which is actually analog to scintillation, another term that's a lot more known in the context of X-ray, gamma ray, scintillation, and other types of high energy particle detection like cosmic rays. So there, we use the free electron to induce secondary electrons inside the structure, which will quickly thermalize to a distribution of non-equilibrium electrons that can spontaneously emit. Depending on the type of materials you're looking at, they can emit via a band gap in a semiconductor or in a defect doped medium via some two-level system transition typically. And there, the modeling of the interaction of the electron with the structure is very different because we're looking at a purely stochastic source of currents, which we'll describe in general by its correlation function, which can be in principle a function of two different positions out of the two currents we're looking at, and the frequency. So now I would like to extrapolate those definitions and see how we can generalize them to the context of nanophotonics. And so I will look at this general framework here, which will accompany us throughout this talk. And so if we take a step back in this framework, we typically combine physical effects from the previous slide with some sort of nanophotonic structures. So this is the full framework, and I'm going to talk about different parts of it in more detail. So if we first look at the nanophotonic structures, we typically think of them as a combination of material and geometrical properties. So in terms of materials, we've been working a lot with dielectrics, semiconductors, also metals. We also have some theoretical work with 2D materials. And then we can pattern them using the entire dictionary of photonic structures that has been developed in the past 30 and plus years. And some of them are shown here. Those are some structures that were measured in our SCM, or more exactly, radiation of which was measured in our SCM. So you see mostly two-dimensional photonic crystals and also 1D grading, made of dielectric, semiconductors, and metallic structures as well. Now, looking at the left part of this framework, we have different moments or different zones where the electron can emit light. And we like to separate them as the glancing interaction zone and the impacting interaction zone, which simply differentiates when the electron flies still in the vicinity of the structure, but before impacting it, versus when it's literally bombarding the sample. In the glancing interaction zone, we recover a lot of those coherent cathodoluminescence effects. And in a nanophotonic context, we can calculate the interaction of the electron with the modes using this master equation. So I will walk you through some of the general terms of this formula here. We calculate the work of the electron on the induced fields in the structure, which we expand over eigenmodes of the Green's dyadic function. There are a few interesting things in this formula. The first one is that we see a clear mode electron overlap, which means that if we want to excite modes of the structure efficiently, we need the electron beam to overlap efficiently with the spatial distribution of the mode. The second term is similar to what I mentioned earlier, this complex exponential. We call it phase matching. More exactly, it's half of the phase matching term, knowing that there will be some other spatially varying complex exponential that comes from the mode electron overlap. And when we combine them together, and we look, for instance, at long interaction of the beam or the electron with the structure, we get the phase matching relation, which is very important. And I'm going to use it a lot in the following to describe some of the effects we're looking at in coherent cathodoluminescence. The phase matching relation relates the phase velocity of the mode with the velocity of the electron. So it means that they must be matched in order to get proper excitation of the mode by the electron. It is very convenient because we can plot at the same time the band of the photonic structure and the band of the electron, which is just essentially this relation. In 2D is going to be a line, and in 3D is going to be a plane along the with an angle that's or slope that's proportional to V, and along the K parallel direction, where parallel means parallel to the direction of the electron beam propagation. So we can actually use this very intuitive geometrical argument to guess which modes are going to be excited by a photon, by the electron in some photonic structures. So this is a very simple example where we're looking at the Cherenkov cone, or more exactly, just a light cone with a refractive index. And above some threshold, this plane, which is the electron plane, can intersect the cone. Typically, if we look at one isofrequency contour, it's just going to intersect it at 2 points. If we look at a slightly more interesting scenario here with a photonic crystal slab, there are different types of modes that exist, typically guided modes, leaky modes in the far field, and also bound states in the continuum, which are very high quality factor modes above the light cone. And you see that by tuning the electron velocity, which changes the slope of that blue line, we can excite more or less efficiently some of those modes. And so even guided modes can be efficiently excited by the electron because of the evanescent tail of the electron near field. What's also interesting is that if we look at some metallic film, surface plasmon polariton can be excited at different frequencies by tuning the velocity of the electron. And if I look at a two-dimensional photonic crystal, I get back to a Smith-Bessel-like scenario. So K is defined up to some harmonics, which you can think of as diffraction orders, and then you get multiple planes that will intersect this complex photonic band at different contours. And so in principle, all of those modes can be excited efficiently given the phase matching relation. We can even simplify this formula in a three-dimensional case with periodic structures. And we get this formula for the amount of energy lost by the electron. And the only thing I would like to highlight is that you see that at the denominator here, we get the group velocity, or one component of the group velocity of the band, which means that in principle, if I shape the band structure of my photonic structure, I can change the amount, I can shape and enhance the interaction of the electron with the photonic structure. So that already indicates that there is a way to do photonic engineering, nanophotonic engineering of electron radiation and electron energy loss. The picture is quite different when we look at the impact interaction zone, and I will mostly talk about what happens in terms of incoherent cathodoluminescence or scintillation. So there, again, we have those fluctuating current sources, and we can still use this Green's function mode expansion to calculate the amount of radiation. More exactly here, we see that we have an integral overlap of the energy loss of the electron with the mode, which means that if we want to pump efficiently, and it's very intuitive, if we want to pump efficiently a mode of the structure, we need to have a strong overlap with where the electron is going to inject energy into the structure. And this is another very interesting opportunity to do nanophotonic enhancement. So in principle, just with this simple picture, there are ways to get nanophotonic enhancements of both coherent and incoherent cathodoluminescence or scintillation. And this is the general idea of this talk, and I will show you how we demonstrated this experimentally. So I will start by showing you some results, or more exactly the setup that we built to record especially free electron-induced radiation in a refurbished scanning electron microscope. So when we started to build the setup, we had in mind that we needed some sort of hybrid optical and free electronic setup. We needed a lot of space to be able to fit samples, especially since we're working at glancing incidence of the electron beam with respect to the sample in Smith-Bessel configurations. Also vacuum compatible optics. And I like to think of this as a confocal electronic optical microscope, where the excitation channel is the free electronic one, and we want to align the beam waist of the electron, where the interaction is strongest, with the optical detection channel. So this is just a nice way to think about it. And when we build our experiments, we need to keep in mind a few high-level physical rules to properly design the experiment. So, of course, the phase matching relation will tell us for a given energy what are the modes that might be excited by the electron. The mode-electron overlap. So typically, if we want to excite efficiently grading modes in a Smith cell setting, we will need to be quite close, like a wavelength close to the structure. So we need the electron to fly fairly close and for a fairly long distance. And I haven't talked at all about material properties yet, but typically if we have materials that charge a lot, like dielectrics, this can be a problem because then we get unstable signal because a part of the beam is always bombarding the structure. The last interesting part that's related to material has to do with the amount of available enhancement. And there's been work also by our group on deriving fundamental bounds on the amount of radiation that can be extracted from free electrons interacting with arbitrary nanophotonic structures. This is just a high-level description of the setup. So when I started to work on this, there were actually very, very few groups that had such a setup. And in the past 5 to 6 years, there's been a lot of work on building similar setups in SEMs and TEMs. Typically, TEMs are much better when it comes to detecting electron energy loss, and SEMs are favored for cathodoluminescence, so direct radiation measurement experiments. So let me just highlight a few important features of the setup. This is the vacuum chamber. This point here is where the electron beam interacts with the sample. The light is directly detected with this microscope objective that's directly into the chamber. Then light gets sent into this area, which is mostly optical spectroscopy detection. In the visible, we also have a CCD camera that images the surface of the sample in order to do proper alignment. We have some excitation channels also to do alignment of the optical detection channel with the electronic excitation channel. And recently, we've started to move towards UV detection. So there we have everything under vacuum up to the UV spectrometer. So those are just pictures of the refurbished SEM as we got it in 2018. And after some work, we built this entire setup. We had to do a few modifications of the SEM itself, namely relocating the secondary electron detector, adding a lot of motorization directly inside the vacuum chamber so that we can move the sample without breaking vacuum, also tilt angles, and typical optical in and out coupling. And the in coupling is mostly used so far to do alignment. Those are the general specs of the setup. So we have up to 40 kV excitation energy, which is a little bit more than most SEMs you will find today for imaging, but this is actually not a very good SEM for imaging. This is really just something we use for this experiment. We have pretty high beam currents. We're using an LAB6 filament, and we have therefore a very large beam size. In principle, we can do detection from 150 nanometer up to infrared frequencies with the setup. So let me show you just like a very simple experiment we first did with the setup. There we were looking at Smith cell radiation in silicon gratings. A lot of the work that had been done on Smith cell radiation was mostly focused on metallic gratings. So we wanted to check that it would work equally well or better with silicon and other semiconductors. And the interesting thing here is that with those periodicities of the grating and electron excitation energies that were available, we could get emission from the silicon grating into the window where it's actually transparent and up to the telecom C-band. If we push this to even smaller electron energy, down to a few kilo electron volts, then we get similar results with shorter pitch gratings. And you see that the signal bandwidth can also be narrowed. And this is because the bandwidth typically scales with the velocity for a given wavelength. So This process is actually pretty inefficient. And one of the first things we wanted to do is use nanophotonics to make this potentially more efficient. And so I will talk about a project where we use nanophotonic engineering of the band structure directly, and especially we use flat bands in order to enhance the coupling between the electron and photonic modes, resulting in greater radiation. So the results are in this paper. And to best explain the concept here, I will go back again to the phase matching relation. So this is a conventional Smith-Bessel or Cherenkov scenario. You have electrons flying in a bulk medium or aloof one degrading. Typically, the modes are excited can be determined by this intersection. So it's a plane with a cone, either a fundamental plane or a shifted plane by some harmonic. But in any case, the best you can get, since you always have a conical dispersion relation, is that the intersection of that plane with the cone is going to be a point at some isofrequency contour. Now, what we propose is to design flat bands in photonic crystals, which is something that's fairly simple to do with Dirac cones at the degeneracy point in 2D photonic crystal slabs. And there we can get this type of band structure. So those are two bands across a Dirac cone. And at some point in frequency, those two, this band structure actually becomes flat along this direction, along the plane direction. So it means that for some kinetic energy of the electron and some frequency, we can get the intersection of that band and the electron plane to be a continuum of modes. So this already leads to some intuition as to why this should be more efficient as a Smith-Bessel radiator, but also keep in mind this formula I showed earlier. You see that this type of band structure typically cancels that component of the group velocity along that direction. So in principle, this diverges, which also indicates that in principle, we should get much stronger radiation. So we actually realized such a structure. They were fabricated by Team Savas with interference lithography. It's a photonic crystal slab waveguide. The periodicity is on the order of a few hundred nanometers. And they were characterized by Yi and Houning. So you see here, those are some simulation results. So indeed, at some frequency, you get a flat contour. Those are confirmed by Fourier microscopy experiments we did here to measure the band structure. You see that there is a flat scattering contour here. And we can look into time domain simulations of the intersection of the beam with the structure to calculate how much radiation we're going to get out of this structure. So when we're off the flat band, if we look into Fourier domain and the K domain, you see that we get this wiggly spectrum here. And as we get closer to the flat band, which corresponds to changing the velocity of the electron here, which corresponds to changing the angle of that plane with respect to the horizontal plane, we get to a point where we have phase matching of the entire plane with the flat band at a given frequency. And you see that we get a very strong enhancement of a continuum of modes around k equals 0. And this is a condition where, again, you have the intersection of the flat band with the electron plane. All right, so we wanted to check that this actually works in experiments. So we went back to the lab with the setup I showed earlier. And the only addition we made to the setup was to add a tilt stage that can control the angle between the electron beam and the photonic crystal high symmetry lines. This allows us to control essentially the other angle of the plane, the electron plane with the band, and typically this effect will only work when you have a perfect alignment of the electron beam with the high symmetry line of the photonic crystal. So those are some electron beam measurements. On the left side, those are numerical simulations taking into account other radiation effects happening into the same sample. And you see that our measurement reproduces fairly well the general behavior here. The main thing we're interested at is to have this peak that happens at a given frequency and at a given velocity. And this indicates in principle that we have flat band enhancement. Let me show you as a comparison what happens when we have a tilt. So now we're no longer aligned with the flat band. We get a much smaller enhancement. And typically, if we compare the enhancement on and off the flat band, we get a factor of 100. So we get 100 times more light out when we get proper phase matching. And as a benchmark or as a reference, we can compare the amount of light we get from a vanilla silicon grating, just without any special optimization. You get a pretty monotonic evolution as a function of the energy, and there's no proper resonant feature at a given velocity and electron energy. So taken together, this is a very strong indication that at some velocity, we did achieve flat band enhancement. So now let me tell you a bit more about, so this was a purely coherent cathodoluminescence type of effect, and I would like to tell you more about how we can use similar nanophotonic structures to enhance this time incoherent cathodoluminescence, and especially scintillation, and I will talk a lot about X-ray scintillation. So perhaps a tiny bit more motivation. Scintillation is actually an extremely ubiquitous effect. Of course, we find it in electron microscopy in the form of incoherent cathodoluminescence, and that's the first thing where I'm gonna show you in the next few slides. Similar effects can be used by pumping phosphors to make, for instance, efficient UV light sources. There's been a lot of interesting work by the Watanabe group in Japan. But very similar physics occurs in X-ray imaging, for instance, in medical imaging, and also in the detection of cosmic rays with scintillators. And the physics that unifies all of those seemingly uncommon effects is the following. So you have a high energy particle, can be an X-ray, can be a high energy electron, gamma ray, cosmic ray. It's going to ionize secondary electrons into the materials to very high levels of energy. They're going to thermalize through mostly inelastic scattering and form a sea of electrons, for instance, above the Fermi level in semiconductor. And then they can spontaneously emit light, for instance, in a semiconductor at the band gap, or via defect states that are doped into the crystal. And really the main part that we're interested in this work is the last part, which has to do with photonics, and more specifically spontaneous emission. And so this work aims at demonstrating that we can enhance spontaneous emission in the context of scintillation light. So when we started this project, we wanted to make a survey of available effects in photonics that could be used to enhance scintillation. The first one that came naturally to mind, and that was actually first proposed by the group of Ido Kaminer at the Technion, is to use Purcell enhancement. But in this very interesting configuration where you have a 1D photonic crystal along the direction of the electron beam for the X-ray propagation, so that you still get a fairly thick structure that can absorb X-rays efficiently. And the local density of states is patterned or shaped along this direction in order to get stronger emission, stronger spontaneous emission in the scintillator layers. So this is a sandwich of a scintillator and some other dielectric structure. And each layer is has a thickness on the order of a few hundred nanometers at most. Another very natural type of effect that comes to mind, especially from the field of photovoltaics, is surface texturing, where we can enhance the amount of light that gets outcoupled into the far field without modifying any of the bulk properties of the scintillator. It was first proposed in the context of photovoltaics by Eli Jablanovic, and then there is a generalization of it into with periodic patterns, especially sub-wavelength periodic patterns for maximum enhancements. But in both cases, the enhancement you expect is on the order of n square, because essentially what you do is you allow some of the lights that would be trapped by total internal refraction to escape from the scintillator or the solar cell. A lot of work was done by Paul Lecoq at CERN on using those types of enhancements on scintillators. And so we wanted to take a step back and propose a general framework to model scintillation, irrespective of the type of nanophotonic effects we want to use to enhance it. So we consider the general picture here, where you have a nanophotonic blob, just patterned on the scale of the optical wavelength. And by optical here, I mean scintillation emission wavelength. And we pump it with a high energy particle beam It's going to induce some fluctuating current sources that emit. And to properly describe the complex effect that scintillation is, we need to bring together different fields of physics. So we first need to calculate the energy loss dynamics that will give us the spatial distribution of the emitters in the structure. We also sometimes resort to density functional theory to calculate the available energy states and the different emission line width, and also potential competition between the emitters. And the last part is purely nanophotonics, and it consists in calculating in the far field the emission pattern from those stochastic current sources. And that last part is actually far from being simple, because you have this stochastic current source. And in principle, the naive way of calculating this would be to do an ensemble average of different simulations, which might be prohibitively costly in 3D simulations. So this is just a framework that we have developed. You can give a geometry of the scintillator, some characteristics of the high energy particle beam, material properties. Typically, it's Z number for the X-ray absorption part and the permittivity for the nanophotonics parts. We use Monte Carlo energy loss and DFT simulations to calculate the spectral and spatial distribution of emitters, and full wave nanophotonics to calculate the emission into the far field. And there's a key element that allows us to calculate scintillation in the far field, which is that we use electromagnetic reciprocity, which enables us in some cases to simplify the calculation of scintillation light to the product of two things. The first one is the spectral function of the scintillator. So this is just the spectral function of the bare bulk scintillator you would get, times a field enhancement function, which is purely nanophotonics. And this is essentially the integral of the induced field in the scintillating volume. The reason why we can do this is that with electromagnetic reciprocity, calculating the emission in the far field from this complex stochastic ensemble of dipoles is equivalent to just sending a plane wave from the far field, from the direction and frequency you're interested in, and look at the induced field. This is a very general observation that has been known in photonics for a while, especially in photovoltaics and calculations of thermal emission, because they share very similar physics with scintillation, which is that you have this stochastic current distribution that you want to calculate radiation from. So we wanted to confirm this framework with actual experiments, and we first did them in an electron beam platform. So this is the same old sample as what setup as what I showed you earlier. And here we're also looking at a photonic crystal slam, and we're going to look at scintillation from self-trap hole defects in silica, which are fairly common defects known especially in the context of silica fibers. So they emit at green and red wavelength with peaks that are well known in the literature. And we compare the emission from a thin film, so without any photonic pattern on the surface, versus with a photonic crystal etched at the surface with different depth. And so you see here that first of all, there's a pretty strong dependence of the photonic crystal etched depth on the red peak, while the green peak is fairly insensitive. The reason is that according to our framework, there's a high quality factor resonance that occurs at red wavelength, which contributes to the enhancement of the red peak when you have a photonic crystal. And our theory overall reproduces fairly well the experiment for both peaks. And you can use this, for instance, to get a stronger peak in the red. And I think that peak to peak gets something like 6 times more light at red wavelength. Okay, so this seems to confirm our framework, at least for electron beam experiments. But what we were mostly excited about was to move towards X-ray experiments, especially given the potential in X-ray imaging. So for those experiments, we hacked X-radia micro CT that we have at the ISN. It's a fairly simple X-ray setup where you have an X-ray source. It's the Bremsstrahlung at 120 to 160 kbp. Scintillator that's objective coupled to a CCD camera, and you can put a specimen in between those two in order to make an X-ray scan. The first samples that we looked at with photonic crystal etched at the surface of a scintillator were fairly thick scintillators, conventional YAXE used in X-ray imaging. This is a pretty bright scintillator emitting at 550 nanometer. And we etched its surface into an array of 2D photonic crystal, like it's just an array of holes. Those were fabricated with a Wraith focus ion beam lithography machine that's at MIT Nano, and Yang fabricated those samples. Even though it's a very, very nice fib, we can only make fairly small scale pattern. So this has some limitations for imaging. And if you have some thoughts on how we could make those patterns much larger at the surface of scintillators, I would be happy to do chat after this talk. And so with this type of photonic crystal, we can actually get very strong enhancement of the amount of light that gets out of the scintillator. This is with a 20 micron thick scintillator, so already for fairly high resolution imaging. And you see that we get almost a 10x enhancement of the amount of light that gets out of the scintillator when you look at on versus off the pattern. This is also reproduced by our theory, which is derived with the framework I presented earlier. And so naturally, the first thing we were very excited about was to put some specimen in the path to see if this actually translated into brighter images. You see some X-ray scans that were performed with nanophotonic scintillators. The bright square corresponds to the area that's patterned with the photonic crystal. We don't see any significant decrease in the resolution, but a much brighter image. So we made a few other X-ray scans with organic and non-organic samples just to check that this was working in a general fashion. Right. So I'll conclude partially, and then I will show you some a lot more recent results that involve nanophotonic structuring of scintillators, and especially novel applications we're looking into X-ray imaging, especially done in collaboration with Ido Kaminer. But for now, let me wrap up. So we developed this framework to calculate scintillation in arbitrary nanophotonic structures and demonstrated it into X-ray and electron beam platforms. And an interesting feature that which I didn't talk about was actually showed to you earlier. If you look at this framework, see that there are some lines, the purple lines, that can also have backward propagation of information. With that, I mean that we can calculate gradients of the outputs with respect to the input, even in this complex emission process that scintillation is. So it means that we can take those gradients, put them into an optimizer, and optimize the shape of the nanophotonic scintillators in order to get optimal scintillation, for instance, if we want to emit light to a particular direction. And so I would like to just highlight very quickly 3 recent publications that were done in collaboration with Professor Ido Kaminer from the Technion, where we took those ideas further by realizing, either in theory or in experiments, some first demonstrations of multi-layer photonic crystal scintillators for enhanced imaging. So the first work is actually focused on breaking a very, very important trade-off in scintillation imaging, which is universal. It's shared by the radiologists and the people who do cosmic ray detection. When you have a scintillator and you want efficient detection, the first reflex is just to make it thick, because it's going to absorb more of the incoming radiation, typically with a Beer-Lambert law. If you make it thicker, if you make it thinner, you're gonna get more spatial resolution. Typically, the spatial resolution scales with the thickness of the scintillator, but then you lose in detection efficiency. On the other hand, you make it thicker, it's more efficient, but more blurry on the detector, so less resolution. And what we propose here is to use those multi-layer 1D photonic crystal scintillator to get at the same time high resolution and high efficiency with the same volume of scintillator as one of those 3 guys, I think the middle one. And you can think of it intuitively as this photonic crystal makes all of the scintillation light, or most of the scintillation light, to go forward and to blur less. And so photonic crystals are known to be able to shape the angular distribution of photons emitted spontaneously. And here we generalize this to scintillators. And I think this is pretty striking when you look at this plot, which shows this inherent trade-off to any bulk scintillator, where you have this hyperbolic function of the efficiency as a function of the resolution, and we can break the trade-off pretty significantly with those inverse design structures. And here, the thickness of each layer was optimized to get optimal performance. So this is theoretical work. I'm going to show you in a few seconds some experiments, but still on the theory and simulation side, We can even optimize directly imaging metrics of interest, like the resolution through the modulation transfer function, the MTF, or the detection efficiency with the DQE, which is an important metric in X-ray detection. It's a detective quantum efficiency. And you see that the optimized designs will get better resolution, which is defined as when this MTF intersects the line at, I think, 3%. And here you get much broader in spatial frequency DQE that's like above a certain threshold as well. We can make simulations of what the imaging performance is, even with adding noise into the imaging setup, which is typical in typical X-ray sources. And you see that overall the optimized sample, the optimized scintillator always does better. Right. And so we really wanted to demonstrate this experimentally. And so there was a lot of work that was done in Ido's group, especially by Netta, on fabricating multi-layer scintillator. And here they developed a modified solid gel method to make a multi-layer scintillator made of silica and a lutetium compound. So this is just a general representation of what the sample is like. If we make X-ray images with it, so here you already see that it's much larger scale. You can imagine an entire ant. This is something it's a deposition method, so it's already like a few centimeters at least. You get a brighter image with the nanophotonic scintillator. A very interesting feature is that you can even make it a faster scintillator. So to be fair, we started with a very, very slow scintillator, but we could still make it faster by using the nanophotonic patterning. And you get directional emission here at off-axis angles because of the nanophotonic patterning as well. This is a fib cross-section of the sample. So you see that one other interesting feature is that despite the very large amount of disorder, despite all the work that was put into fabricating the sample, you still get a very distinct feature at those off-axis angles. And so we did more theory and simulations to understand what was going on. And it seems that at least for pretty thin structures, those effects are also robust to disorder. So this is a demonstration of also the capability in terms of imaging of those inverse design photonic scintillators. So you see here that the PSF is stronger at x equals 0, which just means that you get more photons out. And also the MTF can be better. So you get, in principle, a better resolution. And perhaps to convince you, we can just look at those images of a tip or an AFM tip. This is a metallic grating and just a razor blade. And this is actually how we calculated or measured the MTF. And you see that overall we get sharper and less noisy images with the nanophotonic scintillator. So with that, I would like to conclude with those recent works on nanophotonic scintillators and their first applications to X-ray imaging. I think that those first steps are particularly exciting, given I think the future work that's going to be done in this field, both in terms of fundamental physics and applications. In terms of fundamental physics, I think we're still at a point where there are many, many effects in photonics, especially in nanophotonics, that haven't been used to enhance scintillation. And in terms of applications, I'm particularly excited to see how those nanophotonic scintillators could be used to enhance applications, for instance, in medical X-ray imaging. So let me thank you all of my collaborators, especially my PhD advisor, Martin Sledicic, and collaborators. I see I put Ido twice, so he really mattered a lot. And the funding agencies, and let me thank you for your attention. I'm very happy to take any questions.
Any questions for our speaker?
How did you build the layered scintillator structures?
So I didn't do it myself. It's a modified solid gel method. They do it layer by layer, so it's extremely tedious. And there's a lot of work that has to be done on the optimization of the layer accuracy. So it's not meant to be a very scalable process. It was really just a proof of concept demonstration.
Can you go with the solid gel because something like a vapor deposition, the materials aren't really amenable?
So the reason why they did solid gel is that there was a way to make it compatible with a lutetium compound that was scintillating in a decent enough way, and to make it compatible with a silica layer as well. or it doesn't have to be silica, it can be any dielectric that has a decent contrast and refractive index.
Like the techniques that you talked about using for enhancing the scintillation, I guess, like could those also be used for enhancing emission in like electrically pumped devices like LEDs, spontaneous emission?
Yeah, absolutely. This is something we're looking at actually. So we're looking into two main directions. The first one is related to those UV phosphors. We're trying to see if scintillation or nanophotonic scintillators can be nanophotonic phosphors, I guess we'd call them, can be used to make brighter UV phosphors. And there's another direction that was actually developed in the 90s on doing electron beam pumped lasers. And we're also interested in the detection of this with nanophotonics.
Electron beam pumped lasers, so you're integrating cavity into the structure.
Yeah, so I'm not sure we can call this a cavity. It's usually just a very thin piece of like gallium arsenide or cadmium selenide.
So more of an amplified spontaneous emission.
Well, you do have a lasing threshold. If you pick the right thickness and you make sure. So usually they're pumped from the top and then you have transfers later, like the cavity in the transverse direction. Yeah, there was work. There was a lot of work from Russia on this in the 1990s, and some from Philips as well, the company.
Make like a TV laser tube with that face.
Yeah, absolutely. So I talked with someone who worked on this, and back then they wanted to make an actual TV with like 3 different colors, but apparently it was really hard to make the blue color or the blue color laser because it had to work at cryogenic temperature. So it was really not convenient to make a TV out of it. So we never made it to the mass markets, unfortunately.
Yeah. Regarding the SEM, the electron gun, I don't know how limited you are by like the geometry of your electron beam, but I wonder, like, have you thought about using a field emission gun that would have like a lower divergence angle of the beam?
Yeah, so the typical divergence angle that we have, I think, is on the order of a couple degrees. So that's why, for instance, in the supercritical emission experiment or the flat band experiment, we didn't have like a very strong dependence on the tilt angle. We didn't think of doing field emission ourselves, but we have some colleagues who do in Carl Bergman's group, also at MIT, and they're building a similar setup, but I think they're only detecting the electron energy loss. But yeah, it's also in an SEM. They're working at 10 kV with field emission.
Another question. I had a question. So in these X-ray imaging experiments that you're doing, where is the sample with respect to this nanophotonic structure that is enhancing things? Is it kind of in front, or is it sampled inside, or how is that?
By sample, do you mean specimen, like the thing we're X-ray scanning?
Yeah, exactly. Right.
So we are using a very conventional X-ray imaging configuration. Most cases, if this is the source, this is the detection, so the scintillator and the detection optics, the specimen is usually halfway. The only thing that changes is you get geometric magnification and a cone beam with a cone beam source.
So should we think about, should I think about this nanophotonic structure as effectively like a much better X-ray lens in effect? Because you're kind of sort of like collimating the beam or something like that. But I'm trying to search for an optical analog.
Yeah. So I think the optical analog would be just like a regular projector for the X-ray part. So you're magnifying the object onto the scintillator. But then the scintillator is not doing anything to X-rays, at least in terms of wave shaping. It's really just a converter into visible light, and it's a more efficient converter or a higher spatial resolution converter potentially. Thanks. Yeah.
So I have a question on your X-ray scintillator work. What's the X-ray wavelength, and how does that relate to the, and oftentimes they use the X-rays to measure the interatomic spacing in the crystal and that sort of thing? How is it really for that sort of
So,
wavelength?
yeah, I would guess that in X-ray diffraction, for instance, they use close to monochromatic X-ray sources because you want to have a diffraction effect, right? For most X-ray imaging applications like the one we have here, it's a very incoherent X-ray source. It's like a flashlight of X-rays. It's very broad, it relies on Bremsstrahlung, so you get very broad spectrum from 0 keV up to the acceleration energy of the electron. So, in terms of wavelength, it's going to be sub-nanometer, close to angstrom, but very, very widely distributed. And the photonic crystal itself is really not, it's not patterned at the wavelengths of the X-rays, right? It's only acting on the last step of the process, which is purely optical.
Any further questions?
Should we check if there are any questions on the Zoom perhaps? But I don't see any.
I
Yeah.
haven't seen any thus far. So let's thank our speaker again.
Thank you very much.